Hello friends, welcome to this lecture of data structure and algorithm design. In this lecture, I am going to discuss the rest of the asymptotic notation. Let us begin with big omega asymptotic notation. So, big omega asymptotic notation. If we look at the definition of big omega asymptotic notation, we come to know that big omega gives the lower bound running time it gives lower bound of running time for a given algorithm. Fine. So if we define it in terms of omega, we are going to obtain this very important relation, and here Fn and Gn be the running time, two running time of a given algorithm. So we can say that this is a way we can represent the big omega for two given running time of an algorithm. Fine. If we consider it further, we basically come to know that big omega gives us the best case running time for a given algorithm as compared to the big O asymptotic notation, where we obtained the worst case running time. Here in big omega we basically obtain the best case running time for a given algorithm. If we define it mathematically, so there exists positive integers C and N naught such that Fn always comes out to be greater than or equal to Cgn for all n greater than is equal to n naught. So mathematically we obtain this relation for the big omega, where Fn is always come out to be greater than Cgn for all n greater than or equal to n naught. We can represent this mathematical definition for the big omega asymptotic notation through the graph also. And if we draw the graph for it, we have n as a size for a given algorithm, t as a running time for a given algorithm, and the curve that we obtain basically here is somewhat like this, where we have this curve Fn and this is Cgn, and we can see that there is some point n naught for which Fn is going to be increasing as compared to the Cgn. Fine. So for all n greater than n naught, we obtain the Fn to always in an increasing situation as compared to the CGN, and this basically justifies this mathematical expression. If we look at the limit definition of big omega asymptotic notation, so how we can evaluate the limit definition for two running time Fn and Gn for in terms of big omega notation. So when we evaluate this expression, we are going to obtain the value either as infinite or finite value, but never equal to 0. That is a basic idea that we have to consider under big omega asymptotic notation. So let us understand all this thing through few examples. So let us take the first example as 2n omega 3n omega 3n. So this simply represents that 2n will comes out to be always greater than equal to 3n. Fine? And we know this is never true. So we can say the value comes here out to be false. Fine? So that is the idea of 2n omega 3n. Fine, this is a function fn and this is a function gn. Fine? But if we consider the situation in this manner, then we can obtain the result something like this. And we know this is always true, hence the result will be true. We can also verify it through the limit definition of big omega asymptotic notation. So if we evaluate it through the limit definition, then we come across the situation where we have infinity as a power to 0.66, and when we evaluate this, we always come across the value 0, which is never true in accordance to the limit definition of big omega asymptotic notation. Because in big omega asymptotic notation, we had discussed that the limit definition will always come out to be either infinite or finite value, but never equal to 0. Fine? This fine? Never equal to 0. Hence it is false. Hence it is false. And so it is proved that the definition that we are considering this is never true. Fine? We can also evaluate it through the limit definition to understand whether this is true or false. So if we evaluate Fn Gn, it will be 3n and 2n. When we obtain this, basically we come across a situation where if we evaluate it in the terms of the infinity as a power, we always obtain a very big value, that is in terms of the infinite. Fine? The result is going to come out to be infinite, which is in accordance to the definition of asymptotic notation of big omega. Fine. So it is always true, and so it is hence proved. It is proved that it is always true. Fine. So let us take other cases also. Fine, to understand this concept. So here we can take the example as log n omega log n, and this simply implies that log n is always greater than equal to log n, and it is always true. We can see that it is always true. Fine, that log n is always greater than log n. Fine. We can also take the example something like that. 2 raised to power 2n plus 1 is always greater than equal to omega 2n. If we evaluate it, we come across that 2n into 2 is always come out to be greater than 2n, and we basically ignore it and we come across a situation where we have 2 raised to power 2n, and it is always true. Right? It is always true. Clear? And as we had seen a general expression in the earlier case that 2n is always less than equal to n factorial is less than equal to n raised to power n. And if we consider the log, if we apply the log over this function, this relation basically, so we basically obtain n less than equal to log n factorial is less than equal to n log n. Fine. So if it is f1, if it is f2, and if it is f3, then in terms of the omega, we can represent it as f3 omega f2 as omega f1. Fine. This we can obtain for this order, where this implies that f3 is always greater than equal to f2 and f1 is always greater than f2. So that is a basic idea. This is f2 is always greater than f. Fine. So this is from the big omega asymptotic notation. Fine. Let us now move on to the big theta asymptotic notation in our next lecture.